Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last lecture, we discussed about the space quantization of angular momentum operator. We saw that for a given value of L, we had 2L plus 1 number of angular momentum eigenfunctions. We also discussed how different particles would have different angular momentum, and then correspondingly it will have different angular momentum eigenfunctions. We then wanted to obtain the functional forms of these angular momentum eigenfunctions, and this is where we felt the need of converting our coordinate system from Cartesian coordinate system to spherical coordinate system. And we discussed that instead of when we have a point in the Cartesian space x, y, z, we can redefine that point in a different coordinate system r, theta, phi, where r is the distance of that point from the origin, and theta is the r vector. Theta is the angle that r vector makes with the z axis, and when you make a projection of that point onto xy plane, and that particular vector makes an angle of phi with respect to x axis. Using these three coordinates r, theta and phi, we can define the space of this point in the spherical coordinate. We call this coordinate system spherical coordinate because for a given value of r, if we plot the graphical representation of this system, this coordinate system, we would actually get this graph of a sphere. The possible values of r, theta and phi are shown here. R can go from 0 to infinite. So, this would simply indicate the size of the sphere, the radius of the sphere. Theta, which is the angle between this r vector and z axis, you can see that I can define this when I bring this point anywhere in this direction. The theta value will go from 0 when it is on the when this point is on the z axis, or pi or 180 degree when this is just in the minus z. What about phi? For a given value of r and theta, I can see that I can make a 2 pi revolution around this z axis. I can make a 2 pi revolution around z axis, where the phi value will go from 0 to 2 pi, and I can do this for each and every value of theta. So, for each and every value of theta, when I make 2 pi revolution, you can imagine that I will be getting a sphere. So, therefore, phi goes from 0 to 2 pi, theta goes from 0 to pi, and r goes from 0 to infinite. In this place, you can see the rules to convert from Cartesian coordinate to spherical coordinates and vice versa. For example, if I know the x, y and z value, I can use this relation to get r, theta and phi, and if I know r, theta and phi, using this relation I can obtain their x, y and z coordinates. So, therefore, with using this relation, we can go from one coordinate system to another coordinate system. One very important thing that we must keep in mind is that what is the volume element. So, you remember in Cartesian space we defined our volume element d tau as dx, dy, dz. So, that is an infinitesimally small volume element with dx length, dy length, dz length in x, y and z directions respectively. So, this d tau volume element in Cartesian coordinate converts to this particular form in spherical coordinates. So, this is not simply dx, dy, dz, rather you see when I am talking about r, I have r square dr. When I am talking about the theta coordinate, I have sin theta d theta, and when I am talking about phi coordinate, I simply have d phi. We would actually try to integrate this volume element in the available space. what we want to do is that we want to integrate this d tau from all in the all space. So, I know that I have 3 different integrals to take care. I have r square dr, the second one is sin theta d theta, third one is d phi. R square dr, suppose I am considering a sphere of some radius, let us say a. Of course, it can go to infinite, but I am talking about a fixed value of a. So, this is this limit goes from 0 to a. Sin theta goes from 0 to pi. So, that means for a given value of r, I am taking this r vector from this z axis and bringing it all the way to minus z. So, this is what it happens from 0 to pi, and d phi goes from 0 to 2 pi. That means, for each value of theta, I am making a precision around z axis such that phi goes from 0 to 2 pi. When I integrate this, I have r cube by 3 in the range of 0 to a. When I have this integrate sin theta, I have minus cosine theta in the limit of 0 to pi, and when I integrate d phi, I get phi going from 0 to 2 pi. So, when I use a, I have a cube by 3, 0 would give me nothing. So, I am left with only this term. When I look at minus cos, this minus cosine of theta, minus cosine of pi is minus 1, cosine of 0 is plus 1, and then I have this minus sign. When I solve it, I would get 2, and this quantity is 2 pi minus 0. So, I am left with 2 pi. When I look at this, I see 4 pi a cube by 3. If you remember, this is actually the volume of a sphere of radius a. So, when we integrate over all the 3 coordinates in the spherical coordinates, we get this volume of the sphere, and this is why we call this system as spherical coordinate system. Now, we have defined a spherical coordinate rules to convert from spherical coordinate system to Cartesian system and vice versa. We had in the previous lectures, we obtained the expression for the angular momentum operator Lx, Ly, Lz in Cartesian system, and today what we show here is this is Lx operator in Cartesian space, this is Ly operator in Cartesian space, and this is Lz operator in these are Lx, Ly and Lz operators in spherical coordinate system. So, you see Lx, Ly and Lz, they depend now on, instead of x, y, z or x p x or y p y, z p z, we have the operators depend on some phi related terms, some theta terms. So, there are some differentiation with respect to theta, there are some differentiation with respect to phi. This is for Lx and Ly, and we see that Lz depends only on phi coordinate and not on theta coordinate. Additionally, we can also see the other operators we had defined. For example, L square operator has d square by d theta square or d square by d phi square d by d theta. So, this is the form of the L square operator in spherical coordinate, and these are the form of L plus and L minus operators in spherical coordinates. So, you see that L square depends both on theta and phi, whereas Lz depends only on phi. We will keep this in mind because in our next discussion we will use this argument. These are the definitions of the operators in spherical coordinates. Now, what we do is that since we have defined these operators, now we would be interested in obtaining the functional form of these eigenfunctions of angular momentum operator. The question is, how do we get those functional form? We said we already know that eigenfunctions of angular momentum are space quantized. that means there are finite number of eigenfunctions of angular momentum operator for a given value of L. So, if I have defined L, the angular momentum of a particular system L is defined, then I have 2L plus 1 number of eigenfunctions which are psi L L to psi L minus L. So, for a given value of L, I have psi L L till psi L minus L in the step of 1 where the second index would increase or decrease by 1 unit. So, in this way I can construct 2L plus 1 number of eigenfunctions, where psi L L is the eigenfunction corresponding where L, the m value, has the largest possible value and that value is L. We also know that when I apply L plus operator on this function, which is the uppermost eigenfunction of the angular momentum operator, then L plus operator's job is to take an eigenfunction from its level to the next level. But if I am applying L plus operator on the uppermost eigenfunction, therefore, the result of that action should give me 0. So, in other words, when I take L plus and apply this operator on psi L L, I should get 0. Now, what is the functional form of L plus? L plus functional form is given here. So, I would now use this form. So, I will use this form. I will write h bar e to the power I phi t by d theta. So, these are partial derivative because now I am dealing with two different variables, one is theta and another is phi, I cot theta d by d phi. This is L plus operator and I am applying this on my L L, the uppermost eigenfunction, and I am getting the right hand side as 0. Now, I would spend some time in solving this particular equation. So, I see that these terms can be taken to the right hand side. So, therefore, I have to look at the action of this operator and this operator and this function. So, now before doing that, let us see that the operator has two components, on theta, one is on theta, another is in phi. So, therefore, we would define our wave function psi as dependent on theta part and phi part. What we would do is that we would assume that there exists a variable separation. So, I define that let my total wave function, the eigenfunction, be multiplication of two functions, one depends on theta, another depends on the phi. And I am going to apply this relation instead of writing psi, which is a function of theta and phi, I would use it as s and t, where s depends on theta and t depends on phi. So, when I differentiate this function with respect to theta, I see that I have s of theta and t of phi. So, t of phi will be independent of this differentiation because I am doing a partial differentiation with respect to theta. So, I am left with, and when I do the differentiation with respect to phi, the s function will come out. So, instead of writing psi L L, I just used this definition as s into t. So, then what I would do is that I see there are some terms in theta, some terms in phi. So, I would try to separate the two parts. So, here I have ds of theta by d theta plus equals minus I cot theta s of theta dt of phi d phi, and I bring this t phi from left hand side to right hand side. Now, I would bring this theta related term to the left hand side. So, cot theta when it comes to the left hand side, I have tan theta 1 over s of theta equals minus I dt phi d phi 1 over t of phi. So, you see I can actually separate all the theta terms into one side and all the phi dependent terms on the other hand side. But there is something interesting here. I say that the left hand side has only theta terms, right hand side has only phi terms, but left hand side and right hand side are equal. So, since left hand side depends on one variable and right hand side depends on another variable, and these left hand side and right hand side are equal. So, therefore, both left hand side and right hand side must be equal to a constant, because unless they are constant we cannot satisfy this relation, because I will see that left hand side depends on one set of variable, right hand side depends on other set of variable, and if they are equal that means they both must be constant. We would use this argument and try to work on this problem. We would first take up the theta problem. When I have, so therefore, I write here is a constant. So, since now in this equation I had the terms which were depend on phi and theta, but since I am now only dealing with one variable at a time. So, I can replace my partial derivative to normal derivative. So, I took s theta and tan theta to the other side, becoming cot theta. So, I rewrite this and I integrate both the sides. When I do that, in the left hand side I have ln s of theta c when I differentiate cot theta d theta, I would get ln sin theta multiplied by this c is the constant, plus of course, I will have some constant of integration. If I write down the value of c theta, I would see that both side I am taking care of the natural logarithm, and then I have sin to the power c theta and multiplied by some constant. So, I am instead of writing this equality, I am writing a proportionality, because there is some constant of integration coming. So, I have some idea about this s of theta, which is rather simple as sin to the power c theta. Now, we have taken care of the left hand side term. Now, we would actually go to the right hand side term, because right hand side has only phi related terms. So, to do that I start as the right hand side term had this term. So, the right hand side is also equal to a constant c. Now, the task is to solve this equation. So, again, since I am dealing with only one variable, that is phi. So, therefore, I can replace this partial derivative to regular derivative. So, I have dt phi or I can take this minus I to the right hand side and bring this t of phi to the left hand side, I have now I would integrate both the both right hand side and left hand side. So, when I do this, I have ln of t of phi equals I c phi. So, I am just integrating d phi because I is imaginary root, c is the constant. So, I am getting phi plus that is the constant of integration. So, therefore, t of phi is proportional to E I c phi. So, again I am using this proportionality relation instead of equality because there exists another constant. If you remember what we had, c of theta as proportional to sine to the power c theta. So, we had defined psi L L theta phi as s of theta t of phi, and now what we get is that some constant, because each of them will have some constant term. So, I collected them and I am writing that constant n here, sine to the power c theta e to the power I c phi. So, this is the functional form that I am getting for the angular momentum eigenfunction for a particular angular momentum eigenfunction. And what is that? When n takes the maximum value. So, this is the eigenfunction, the uppermost eigenfunction for a given value of L. But what we see here, we will realize that there is a sine function, we realize that there is an exponential function. But what is, and we also know theta and phi, but what is should be surprising is that what is this c? We still do not know what is c, we have not defined c, rather we said that this c is constant. And how is this constant related to our problem? To do that, let us see what happens when I apply Lz operator on this psi Ll. We know that psi Ll is an eigenfunction of Lz operator with an eigenvalue of Lh bar . The functional form of Lz operator is minus IH bar d by d phi. When I apply this functional form of Lz operator on this form of psi Ll that I just got, you would see so I see this is a differentiation, partial differentiation with respect to phi alone. So, therefore, theta term and this n term will go out, and when I do this I would have n sine to the power c theta minus I h bar, and now I am differentiating e to the power I c phi with phi. So, I have I c and e to the power I c phi. I can rearrange that as n sine to the power c theta e to the power I c phi, and I am left with this minus I plus I is 1. So, I am done with C h bar. So, you see in the left hand side I have this operator acting on this function which is an eigenfunction. In the right hand side I have got back this function multiplied by this constant, and this constant is nothing but the eigenvalue. And here when I make them equal, so you can see C is equal to L. So, since C is equal to L, I can now write the general form of psi Ll as n, the constant, sine to the power L theta e to the power I L phi. This is the general expression for psi Ll. So, when L equals 0, psi 0 0 becomes n sine to the power 0 theta. So, this is 1 e to the power I L phi, L is 0. So, this is 1. So, psi 0 0 is simply n. What is n? N is a constant. How do we determine that? We have to normalize this. When L equals 1, we have psi 1 1 as n, the normalization constant, sine to the power L theta, L is 1. So, sine theta e to the power I L phi, so e to the power I phi. When L is 2, we have psi 2 2 as n sin square theta e to the power 2 I phi, and so on so forth. So, for different values of L, we have obtained now the wave function, but one thing that is not known yet is the normalization constant n. In next lecture, we will start from this point and then we would see how we can normalize these state eigenfunctions and what are the normalization constant. And another important thing is that we are still getting only LL. This is the functional form of an eigenfunction of one of the 2L plus 1 eigenfunction corresponding to angular momentum L. So, therefore, what about the rest of the angular momentum eigenfunctions? These are some of the unanswered questions in this class, and we will take them up in our next class. Thank you for your attention.